So here's the last bit of sneakiness that we can play with atoms. Surely now, we're going to get to grips with it. Leave the detector there, but just very quietly go and unplug it. Don't let the atoms know that you're not spying on them. Make them think that you're still detecting them. So, yeah, okay, we're going to run the experiment, atoms, okay, get ready, one at a time, we're going to be checking on you. All right, so run the experiment again. Now, if you can explain this using common sense and logic, do let me know, because there's a Nobel Prize for you. Quantum mechanics is the most powerful theory in the whole of science. And as a physicist, I mean, okay, the biologists may disagree, but it beats Darwin's theory of natural selection with one hand behind its back. Because quantum mechanics underpins so much of physics, pretty much all of modern chemistry, and therefore potentially biology. Without quantum mechanics, we wouldn't have electronics, we wouldn't understand what a semiconductor is, we wouldn't have lasers, we wouldn't have most of modern technology that we use today if quantum mechanics wasn't right in explaining the rules of how the microscopic world behaves and how atoms fit together. And yet, at its heart, it is incredibly mysterious.
But at its heart, quantum mechanics is strange. So strange that one of the founding fathers, Niels Bohr, once said, if you're not baffled by quantum mechanics, then you haven't understood it. You have to think, how can that be? If you think, yeah, okay, yeah, I get it, you haven't got it. Because it really is ungettable at a sort of common sense level. It really is strange. Quantum mechanics really does say that an atom can be in two places at the same time. One atom. Weirdly, when you look to see which places it really is, it'll disappear in one place and pop up in the other. So how do you know it was in two places at once? We can design experiments that will prove that had it not been in both places at once, you wouldn't get the results that you'd see. An electron, the tiny particle that orbits around an atom, spins. Not in the way that the Earth spins on its axis, but in a rather strange way, to the extent that an electron, when we are not looking, is spinning both clockwise and anti-clockwise at the same time. It sounds like, oh, you boffin physicists come up with all this nonsense. How do you know that's what really happens? And without that, we wouldn't have so much of modern science. Any one of you who uses any device, smartphones, TVs, computers, anything with a chip, all rely on quantum mechanics. Without quantum mechanics, we wouldn't have understood the nature of matter. We wouldn't have understood the nature of semiconductors. Therefore, we wouldn't have developed chips. We wouldn't have computers. Most of modern technology today relies on quantum mechanics. And yet, at its heart, it's very, very strange. Well, I've said, biology at its heart is chemistry, and chemistry is basically quantum mechanics. So surely biology ultimately relies on quantum mechanics. Well, it does rely on quantum mechanics in the sense that quantum mechanics describes how the atoms fit together to make the molecules of life. But this new field, this field of quantum biology, is really asking whether the weirder aspects of quantum mechanics play a role in biology.
Now, quantum physicists have had almost a century to get their heads around this, and in a way they have, because the mathematics of quantum mechanics is perfectly well developed, and it's very powerful and predictive, and it helps us explain the subatomic world. But we've got something like half a dozen different ways of explaining how those atoms get through the slits. None of them are very satisfactory. The standard one, believe it or not, the standard way of explaining it is to say, don't worry your pretty little heads about how that atom does it. You can never know. All quantum mechanics ever tells you is it makes predictions about the results of experiments when you go and observe something. So quantum mechanics will indeed, the mathematics will tell you, if you're not looking, you'll get the interference pattern. If you're looking, it'll disappear. And hence you hear, if you've heard in popular science, talking about the role of the observer is central. And it leads to all sorts of wacky ideas like, in the nature of consciousness and so on in quantum mechanics. So quantum mechanics is weird. There's no getting around it. It's not that it's just weird in biology. It's weird for physicists. And it's sort of time that physicists let the biologists know that, you know, we've had all these years of sleepless nights and worrying how atoms do these things. It's about time you know, got very, very concerned about the subatomic world. One process that I have been interested in recently is called quantum tunneling. And I would say it's sort of halfway between mundane quantum mechanics, which is the rules of quantum mechanics that you have to apply in organic chemistry to describe how molecules fit together, including those molecules in living cells, and the more outlandish quantum behavior, superpositions and entanglement and so on. Quantum tunneling is the process whereby a quantum entity, a quantum particle, can somehow punch its way through a barrier, a force field, an energy field that it has no right to be able to get through. In the everyday world, it's the equivalent of me running straight through that wall, disappearing and appearing on the other side. It doesn't happen. In the quantum world, it seems that it does happen. And in fact, the picture I've got here is of the sun. The reason the sun shines, therefore the reason we are here, is thanks to quantum tunneling.
Αυτό το πήγαινε έλα, το οποίο λέγεται μετασάρκωση, στην πραγματικότητα δεν είναι τίποτα άλλο παρά η τεμαχισμένη εμπειρία μας ενός πράγματος που τα αντιλαμβανόμαστε με δύο διαφορετικούς τρόπους. Σε δύο πόλους, ας πούμε. Είναι σαν ένα ζευγάρι το οποίο έχει ο καθένας τον εγωισμό του και δεν μπορεί να δει τον εαυτό του ζευγάρι. Ο καθένας ζει στον προσωπικό του κόσμο. Δεν συγκοινωνούν, δεν επικοινωνούν σε ένα κοινό χώρο. Με τον ίδιο τρόπο δεν υπάρχει κοινός χώρος ανάμεσα στο κάτω και στο πάνω, γιατί αυτό εδώ πέρα, η σκάλα αυτή που ενώνει το κάτω και το πάνω είναι κλειστή, δεν είναι ενεργοποιημένη. Και έτσι άλλοτε είμαστε στην ύλη, άλλοτε είμαστε στο πλάτωνα το χώρο και ξανά στην ύλη και ξανά στο ψυχικό πεδίο. Και έτσι δεν ξέρω, δηλαδή όταν συμβαίνει, όταν αυτά τα δύο έρχονται σε κάποια στιγμή μαζί και ενοποιούνται και δημιουργείται αυτή η έκρηξη, τότε λέμε, τότε υπάρχει μια ροή ανάμεσα στο ένα και στο άλλο και βιώνεις αυτό το κοινό δυναμικό που συνεχώς πάλεται κάτω πάνω τόσο γρήγορα ώστε βρίσκεται συνεχώς και κάτω και πάνω και είναι αφυπνισμένο συνεχώς παντού, σε όλο τον κόσμο και σε όλη την ύπαρξη και σε όλους τους ανθρώπους και σε όλα τα άτομα και σε όλο το χρόνο και σε όλο το πραγματικό και το ιδεατό.
I remember you said that death is psychologically just as important as birth, and like it's an integral part of life, but surely it can't be like birth if it's an end, can it?
Yes, if it's an end. And there we are not quite certain about this end. Because, you know, there are these peculiar faculties of the psyche that it isn't entirely confined to space and time. You can have dreams or visions of the future. You can see round corners and such things. Only ignorance deny these facts. It's quite evident that they do exist and have existed always.
Όταν αυτά τα δύο έρχονται σε κάποια στιγμή μαζί και ενοποιούνται και δημιουργείται αυτή η έκρηξη, τότε λέμε, τότε υπάρχει μια ροή ανάμεσα στο ένα και στο άλλο και βιώνεις αυτό το κοινό δυναμικό που συνεχώς πάλεται κάτω πάνω τόσο γρήγορα ώστε βρίσκεται συνεχώς και κάτω και πάνω και είναι αφυπνισμένο συνεχώς παντού, σε όλο τον κόσμο και σε όλη την ύπαρξη και σε όλους τους ανθρώπους και σε όλα τα άτομα και σε όλο το χρόνο και σε όλο το πραγματικό και το ιδεατό. Και δεν ξέρεις που... Δεν υπάρχει κάποιο... Αυτό που βιώνεις, δηλαδή δεν είναι ότι δεν υπάρχουν τσάκρα. Αυτό που υπάρχει είναι το ένα, η ενότητα. Αλλά